Hiya, I'm just let you know I'm recording this. Seems like it's just being me, Sadie, but obviously more people will join us as and when they get their Zoom switched on. So I'm recording this, so if anybody misses it, you can always watch it on YouTube anyway. What I'm going to do is it's the same drill as always. I'm going to sort of go through the questions one by one. I'm probably going to be quite quick with some of the questions where the questions were well answered. It'll just be the odd questions where I think that I need to spend a bit of time on concentrating on the odd sort of questions where maybe what I marked was not quite so well answered. So as I said, getting up to a really high level. Almost every paper that I've received on this occasion was a distinction level, showed distinction level work, which is fantastic. We'll see how we go with that. Don't forget your exams are next week. Your final sort of UFP exams are next week. You should have your timetable, which was sent to you some time ago by Mrs. Randon. If you haven't, you need to email Mrs. Randon very urgently because they start on Monday. They'll be in the King's Hall, don't forget. So your last paper, this is your last walkthrough paper. We've done 8 practices using a variety of UFP and A-level questions. So the chances are when you come to do your final UFP, you'll find that the questions on the final UFP paper will probably be very, very similar to some of the questions you've encountered in the past. So as we're going through to question number 1, what I saw was basically you remembered to talk about the uncertainty or sensitivity of the various pieces of equipment. So the mass balance, the sensitivity was plus or minus 0.010. Okay, sorry, I do apologise. Slight senior moment, must be morning. 0.001 kilograms. Do remember to put the units in. It's the only criticism I have. And here the flight time is plus or minus 0.1 seconds, which is reasonable if you're timing manually. Calculating the mean value, I was really pleased to see that people remembered to keep it to 3 significant figures, 20.2. Thank you for that. So the next one was calculating the percentage and absolute uncertainty. This is an area where we're definitely making improvements. So looking at the past paper sort of question, looking at your answers, most of you are getting this now. So it's the uncertainty in the time, and it's the repeated values. So it's the range over 2. So the range is going to be from 19.6 to 20.6. So 20.6 minus 19.6 over 2, which is 0.5. Some people made a little bit of a mistake where they used 20.4 instead of 20.6, but that was only loss of 1 mark with that. So that's your absolute uncertainty. So it's 0.5. Now you've got to put the plus or minus. It's the only criticism I have of the answers I saw. And, the second criticism of the answers I saw was to remember to put in the units. It's important to do that. Now your percentage uncertainty, here I'm asking for it expressed as a percentage, not a decimal in this case. So you have to look out for that. If you see that percentage sign, it has to be expressed as a percentage. So to get the percentage uncertainty, it's the absolute uncertainty divided by the mean value, which comes out to be 0.025 multiplied by 100 gives you 2.5%. Now, because I've put the percent there, you don't have to write it in again. So that the numbers part of that was done reasonably, was done very well. Just remember the little bits of etiquette. Just really, it's just good etiquette and a good habit to have. So the next question, you're given a standard formula. It doesn't matter what the formula is. You may have come across it before, or you might not. It doesn't matter. You're told that the flight time is related to the mass of the fuel using this formula with some sort of arbitrary constant. Now it says calculate the value of k given the correct units and expressing your answer to appropriate number of significant figures. So really, this is not for the calculation. I mean, you can do the calculation itself in your sleep. You know that k is equal to t squared over m. So t squared was 20.2 squared over the mass, which was 0.01. So if that's the case, you end up with 40804. Now it wants the answer with the correct units and the correct significant figure. So that's what the mark's for. You have to get both of those right to get the mark. Quite a few people lost the mark just through not reading the question correctly. So significant figures. Well, if you look at this, this is actually 1 0. That's 2 significant figures. Here you've got 3. So it's reasonable to give your answer to 3 significant figures. So you round it off to 3 significant figures. And you also got to think about the units. So the units is t squared over m. So the unit of time is seconds. So it's second squared. M is a mass. So it's kilograms. So it's second squared per kilogram. Okay, and that's the correct answer. You did not get the mark if you didn't round off or you didn't use the correct units. Number 2, part 2, sorry, to give the absolute uncertainty of the pupil's value of k. Now again, you can do this by calculating maximum and minimum possible values. I prefer the direct sort of percentage calculation. So we will calculate first of all the percentage uncertainty in k. Well, as k is t squared over m, it's the 2 times the uncertainty in t, which we worked out before to be 2.5%. Express it as a decimal, and you add the percentage error in the mass. Now the mass is given to you as in the table. It's 0.10, and the precision is 0.001. So we know it's going to be the precision, because it's not a repeated value, divided by 0.01. So that's going to be 0.05 plus.
Sorry.
Yep.
Sorry. When are we going to, like, when would we have to subtract percentage uncertainties in this situation?
When would we what? Sorry.
When would we have to subtract percentage uncertainty?
You would never have to do that.
So what if the formula we're not dividing, like for instance, in the formula we're multiplying or something?
You still add the percentage errors. Remember, if you're dividing or multiplying, you are adding percentage errors. Okay?
How about subtracting?
Never subtract. Oh, so when you're adding or subtracting 2 values, you mean?
Yeah.
So all you're doing, if you're adding and subtracting 2 values, all you do is you add the percentage uncertainty. Sorry, the absolute uncertainties.
Oh, okay.
Okay. Thank you for asking. So that's so this value here comes out to be 0.1. So it's 0.15, which is 15%, but it wants the absolute uncertainty. So it's going to be the percentage uncertainty as a decimal multiplied by the value, and the error carries forward. And it comes out to be, I made it 6,121. Well, I would say plus or minus 6,100, I think would be a better sort of level of, a better uncertainty to actually put in there. And remember, it's going to be seconds per kilogram, seconds squared per kilogram. So you do have to remember your units. In this case, it's not asked for the units, so you're not penalized for the units twice, but you should realize it's a 3-mark question. So 1 mark for using correct technique, 1 mark for working out that it's 15%, 1 mark for then multiplying that 0.15 or 15% of your answer to the previous question to get an answer. So the error can carry forward here. Part 3, the student suggests that they use a more sensitive mass balance. Discuss whether you think it's to improve the accuracy of the result. Now, normally timing is your greatest source of uncertainty. But if we look at the 2 percentage in uncertainties here, your percentage uncertainty in t squared is 5%. But in the mass of the fuel, it's actually 10%. So actually, yes, you would want to make sure that you would use a more sensitive mass balance. So yes, it would increase accuracy. Well, it should be precision actually. Okay, because it is the greatest source of uncertainty. Okay, so that is your that's your sort of qualifying statement. So 1 mark if you said it would increase it because it is the greatest source of uncertainty, or it's got a greater uncertainty than the uncertainty in time squared. So that is it gives you, it contributes more to the overall percentage uncertainty than the time does. So it's a little bit of a tricky one. It was a little bit of an odd one. Normally timing is the greatest source of uncertainty because you're timing manually. Right, so on to the next part. Some of you who are sci-fi fans who like the Avengers and Guardians of the Galaxy might recognize the spacecraft here, the spaceship. It's the image is copyright of Marvel Comics, obviously. So we've got some data which has been sort of it's ballpark numbers. They are usually realistic to the calculations. However, in this case, it's science fiction, so there's like to be a little bit of a what we call a poetic license on that. So the first thing is to show the maximum acceleration of the spaceship is 40 meters per second squared. So we're not given very much. It's flying through space, so we're not having to worry about gravity. The maximum acceleration of the spaceship is going to be, well, we use F equals ma. This is pretty well answered, so I'll just go over this quite quickly. A is F over m. So quote the formula, rearrange, substitute. Now be careful. It's 70 times 10 to the power of 6, and there are 2 engines. So we have to multiply it by 2. Divided by the mass, which is 3.5 times 10 to the power of 6, which comes out to be exactly 40 meters per second squared. Very, very easy 2 marks if you do it correctly. Then you have to calculate the time taken for the ship to accelerate from rest using that value of acceleration to 8 times 10 to the power of 6 meters per second. So that's a couple of % of the speed of light. Which often happens in sci-fi movies. That people, so the spaceships travel very close to the speed of light, but we can actually get a realistic value out of that. So we're using SUVAT. Most people got it right, so I'm not going to spend too long on it. But most of us realize we don't have the distance of the acceleration. We have the initial speed because it's from rest, so it's 0. We have the final speed. We're given it there. We have the acceleration because we calculated it. We want t. So we're using v equals u plus at from our SUVAT equations. So t is equal to v minus u over a. Just rearrange it. Substitute. So that's 8 times 10 to the power of 6. Minus 0. So I'm going to ignore that bit. Divided by 40 gives you 200,000 seconds, which is a very long time. Okay, so that's realistically what a spaceship, the sort of time that spaceship would need to accelerate to a speed close to the speed of light, which is where science fiction sort of falls down. The next part is to calculate the distance traveled while accelerating to that speed. So again, we're using SUVAT equations. The easiest one to use is v squared equals u squared plus 2as, but I always give credit where the method has been correct. So even if you've used an alternative method, absolutely fine. So I'm going to work out the distance travelled. So S equals V squared minus U squared over 2A. Substitute 8 times 10 to the power of 6 squared minus 0 squared over 2 times 40, which gives you 8.0 times 10 to the power of 11 meters, which is a very long distance indeed. Okay. So we're looking at a long time and a long distance. Well, it's accelerating to a very high speed. So part B, the spaceship is designed to travel in space where there is no air. Explain in terms of forces why there's no top speed. Now, most people got at least 2 of the marks out of it, but not the 3rd mark. So the first thing is there are no drag or air resistance or friction forces. So the acceleration force, or the net force, is constant. Okay, and since force is equal to mass times acceleration, the spaceship will continue accelerating. The bit that people missed out on was really just sort of using Newton's second law of motion here to sort of link the acceleration and the force. Most people said there's always going to be a constant force because there's no drag forces, but just didn't quite link the force to the acceleration. Calculating the kinetic energy of the rocket, this was trivial. Half mv squared is kinetic energy. So it's substitute. Mass is 3.5 times 10 to the power of 6 multiplied by v squared. So that's 8 times 10 to the power of 6 squared, which gives you 1.12 times 10 to the power of 20 joules. Pretty simple, very easy. Okay. Part C, the spaceship slows to 5 times 10 to the power of 4 meters per second and turns its engines off. The spaceship then enters the atmosphere of the planet. Explain why the spaceship then slows down to a smaller constant speed or a terminal velocity. Now it says it slows down. So this is a little bit different to sort of skydiver free falling. A skydiver free falling starts from rest and accelerates. Here it's slowing down. So why is it slowing down? It must be decelerating. There must be a resistive force, which is greater than its weight. So the first statement is that air resistance is greater than the weight. Now that implies that there is a net force upwards. Which implies that the spaceship will decelerate. So it's the idea that the force upwards is going to be greater than the force downwards initially. And this happens, it decelerates until eventually the speed is reduced until the air resistance or drag equals the weight. Okay, so we're explaining why, aren't we? Yeah, so it's 2 marks, one for mentioning the idea that we're starting off with air resistance being greater than the weight, and then the idea that eventually the 2 forces balance out because the spacecraft has slowed down. Okay, now I gave 1 mark if people who gave a sort of a generic description of terminal velocity. Right, the next question, it says the spaceship falls at terminal velocity through a change in height of 2,000 meters in a time of 5 minutes. So if it does that, you have to discuss whether the ship is in equilibrium. Well, if it's in equilibrium, if it's traveling at a terminal velocity, that's a constant velocity. If it's a constant velocity, it implies that the acceleration is equal to 0, which implies the total net force is also equal to 0. So it must be in equilibrium. Just because something's moving doesn't mean it's not in equilibrium. Remember, equilibrium is the idea that the net force on an object is equal to 0. Then part 3, calculate the average speed of the spaceship at terminal velocity. Well, that's pretty easy. It's pretty trivial, this one. It's only worth 1 mark. So speed is distance over time. It's a constant velocity, so we don't have to worry about acceleration. So distance, it said, is 2,000 meters. Time is 5 minutes. So it's 2,000. And as we're doing a slightly high level, we've got to convert the time from minutes to seconds. So multiply that 5 by 60, and we get approximately 6.7 meters per second. Okay, and that's a little bit slow for my, in my view, but that's fine. That's basically how you do it. And this one was well answered, so I'm not going to spend a long time on it. Now the next question, here we go. Collision. You should always go into momentum mode, but you've got to think very carefully here about direction. People made mistakes here because they didn't think about direction. 2 blocks are moving towards each other. Here they're moving away. They've got a mass of m and 3m. So you've got a description of the experiment here, and you've got sort of a picture before and after here. So the first question is to use Newton's third law to explain why during the collision the change in momentum of block A is equal and opposite to the change in momentum in block B. So most people got 1 mark. Got 1 mark for either quoting or applying Newton's third law of motion. The idea that the force on block A is equal to the magnitude of the force, force on block B. But then we didn't really link it to change in momentum. Well, change in momentum it's got to be equal to force times time. So because it's equal to force times time, obviously, when these 2 blocks collide, they'll spend a bit of time in exerting a force on each other. Now, if you think about it, it's logical that this block A will exert force on block B for the same length of time as block B exerts its reaction force on block A. So both blocks spend the same time in contact with each other. Okay, which implies same change in momentum. That's the bit that people missed out here, was just linking that Newton's third law of motion to the idea that if the force is the same, the time's the same, so the change in momentum will be the same. So then you have to determine speed v. So this is a collision question. So when you get a collision question and you're using the principle of conservation of momentum, we're ignoring friction forces because it doesn't mention friction forces, so we can imply that they are pretty much the same, because it also says here that it's a frictionless surface, so it's an isolated system. So what we really want to do is have a before and an after. So before the collision, the total momentum is 0.4 times 3m. Now here, the velocity is negative because it's the opposite direction. I'm assuming going from left to right is positive, so if I'm going right to left, that's negative. So that would be minus 0.25 times m. Whoops, sorry, there we are. Okay. And it's going to be equal to the momentum afterwards. So here it's 0.2 times 3m. Plus, because it's now saying the block is moving from left to right, this block B, this second block, block B, is moving from left to right, this is going to be positive. So it's plus V times M. So the first thing you can do in this solution is you can cancel all the M values by dividing both sides by M. It gets rid of it. There we are. So they all cancel. So in this case, 0.4 times 3 is going to be 1.2 minus 0.25. It's going to be equal to 0.2 plus V. So we're just really solving this. So this is going to be 0.95. Well, I'm going to keep it as a complete calculation. Divide both, sorry, subtract 0.2 gives you a velocity of 0.35. Okay, so it's pretty simple to do once you've actually, once you've actually sort of, oh, sorry, number 2. Yeah, that's correct. Yeah, so that then gives you your sort of your final velocity. You can check it with your calculator, make sure it's right, but I did that earlier, and it seems to come out correctly. So I'm going to assume that's correct. Now, the next part, you had to calculate for the blocks the relative speed of approach. So to calculate the relative speed of approach, well, this block is moving at 0.4 meters per second, and this block is moving at 0.25 meters per second. So imagine you are stood on top of that block, okay? If you didn't have the ground, then this block would appear to be coming towards you at 0.65 meters per second. You have to add them together because it's 0.4 plus 0.25. So I'm just going to go back. I did do it correctly, but I skipped a step. This should be this part here should be 0.6, so I forgot to multiply by 3. The answer is correct, but I just skipped a step accidentally when I was showing you the working. Okay, so I apologise about that. I can sometimes make mistakes. Now, the relative speed of separation. Going back to this question, a little bit disjointed, but never mind. Now this is moving at 0.2. But this is moving at 0.35 meters per second. So if you imagine you're stood on top of that block, you're kind of not quite catching up to this one. So this is moving away, but moving away a bit more slowly than the actual speed, its actual velocity relative to the ground. So you ignore the ground. This would be 0.35. So you're going to need to subtract the two numbers. And what's the speed of separation? So the direction's implied in there, so we don't have to worry about negative numbers. We end up with 0.15 meters per second squared. Now, simply, this is an inelastic collision. The two ways of actually stating and explaining it are, well, first of all, you could calculate the kinetic energy before and afterwards, before and after the collision. If you calculated the kinetic energy before and after the collision, you'd find that the two were different. You'd have more kinetic energy before than afterwards. You can calculate it. I'm satisfied that you know how to calculate kinetic energy because I've seen that before in your previous answers. So I'm not going to go over that. The other way to do that is an odd thing about elastic collisions is actually when you have an elastic collision, the speed of approach is equal to the speed of separation after the collision. it does come out in the wash. Those of you who are keen mathematicians could actually prove it, but I'm not going to, because it takes ages. But basically, you could actually use that as an argument if you wanted to take a bit of a shortcut. But what you really should have done was calculated the total kinetic energy before and afterwards. But I was happy if you just said it was inelastic, because it's only 1 mark. Right, on to the next question, and I am going to grumble. I'm going to grumble at you over this one. Most of you made a silly mistake. When I saw these 2 values were correctly calculated, so I'm not going to write them down. I do have them on my notes here. But most of you, for your means, wrote that. Does anybody know what's wrong with that as an answer? Anyone?
It's not to 3 significant figures.
Yeah, all these values, there's a typo in there, but never mind. All these values are to 3 significant figures, apart from this one, which is 2. So you should put the point 0 at the end like that. Many of you lost a mark, and it was a silly mark to lose. Okay, but you did do your calculations correctly for your mean height and also your d squared. So then you had to use the graph paper on the next page to draw a graph of height on the y-axis versus d squared on the x-axis. Now again, this wasn't as good as some of your other graphs, to be honest. One of the things about the height is that height doesn't go below 6. So really you're looking at between 6 and just under 10. Okay, so you're looking at going from the y-axis from 6 to 10. For your d squared, you're going from 16 to 324. So you can put the origin, the 0 for your x-axis, but it's inappropriate to put 0 to have the origin for your y-axis. It's not appropriate. Okay, because your lowest value is a long way from 0, particularly when you compare it to your maximum value. So really, for your h, you should have started at 6. Now, if you make every 2, it turns out when I did it, make every 2 squares equal to 1 meter, then actually it fits quite nicely. And again, on the x-axis, you're going up to a value of 324. So if you look on your x-axis, you go from 0, 100, 200, 300. Well, just before here, we get up to about 360, 370 or so. So that, sorry, 340 or so. So it will fit, okay? And it does just about fit. If this was a little bit compressed, but this one wasn't, you got the scale mark anyway. The rule of thumb is that you're meant to be trying to occupy as much of the graph paper with your data as possible. Here I go almost all the way to the top. Here I go almost all the way to the right-hand side here. The scale has to be a sensible scale, i.e. easy to read. So not going up in 3s or anything like that, or 7s. But it has to be suitable to use them and make maximum sensible use of the graph paper. I can give a little bit of leeway when I'm marking it, but not as much as I would have had to have given to give the mark. So that was the only thing that I think people made mistakes with, was that they just didn't get that scale right. And that's why we do so much graph practice in physics. Yeah, when you return to face-to-face teaching after your UFP exams, we're going to be plowing straight into practicals and practical skills. In fact, I might actually do a practical with you that we couldn't do because we're in lockdown. So as we're doing this experiment, as we're doing this sort of graph, most of you plotted the results correctly. Most of you drew a correct line of best fit, so that bit was all right. Most people got 2 or 3 marks out of the 4, but it was a very strange thing to lose a mark on was the scale. So the next part of the question then asks you to calculate the gradient of the graph. Now, for the gradient of the graph, what I need to see for 1 mark, for the technique mark, is a good big triangle, more than half of your line, please, and a measurement. And then for your sort of your gradient measurement, you had to use that same idea of y1 minus y2 over x1 minus x2, measuring y1 and y2 as accurately as possible. Here it was 9.4, here it was 6.6, x1 was 50, and x2 was 280. So it's a simple substitution. Now, the other bit is to remember that x1, because it's a negative gradient, you're expecting a negative number. And when I did it, it came out to be minus 0.0122. Now, here's where people lost marks. Units, okay? If the question says giving appropriate units, then you need to use your units. So the y value, remember, was d squared. So it's the units of d squared would be in meters squared, and the x value was height h, I believe. Is that right? Did we get that the right way? Sorry, the y value was h, and the x value was d squared. So it's mass over mass squared, which is, so meters over meters squared, which is meters to the power of -1. And there's your correct answer. Should be about 3 significant figures, must include the unit or you don't get the mark. Now the next question gives you the formula. Now this is my draft version, which had a mistake in it. I just copied and pasted the wrong formula. This was the correct formula, and indeed the one that you received on your scripts. Ooh, someone joining us. There we are. Now, if that's the case, you're basically asking, does it support or undermine the formula shown? So what we're looking for, well, that g over 800 is a constant. We're using y equals mx plus c. We put d squared on the x-axis. You put h on the y-axis. So that gradient is g over 800, which is constant. So that's going to be a straight line. And the intercept, the y-intercept, is going to be 10. So when you look at your graph, you're looking for a negative gradient. Well, yeah, it's a negative gradient. It goes down. The graph goes down. It's a straight line. And the y-intercept was roughly 10. If it's a little bit out, it doesn't matter. If it's sort of 8, then it probably undermines it. But the y-intercept there was 10. So here it's supported. Okay, it's supported because, well, first of all, we've got a straight line because it's following a straight line graph rule. It's negative gradient. And its y-intercept equals 10. Okay, so what I needed was particularly the concept of the fact that there's a positive y-intercept and the idea it's a negative gradient. That's what we needed to get the other 2 marks. 1 mark was for just saying it's supported. It then says, hence, that means using something to do with the previous question, using your value for gradient of the graph, calculate the acceleration due to gravity. So as with yesterday's masterclass, here, this part here, let me get another color out. This part here of that minus g over 800 is the gradient. It's the m part of y equals mx plus c. So the first thing you would say is that the gradient equals minus g over 800. Okay. So then to rearrange to make g the subject, well, g is equal to 800 multiplied by minus the gradient. Substitute. 800 multiplied by, well, the value for the gradient was 0.122. In my case, yours will be slightly different, which gives you in my case, 9.74 meters per second squared. As long as the value was reasonably close, I accepted it. But for the 2 marks, really, I wasn't really after that bit. I was after the idea that you identified what the gradient was in the formula, and that you then sort of showed some correct calculation using your gradient value. Some of you are still trying to use values from by reading from your graph. Although it's possibly valid, it's not what the questions ask, because the question specifically says using your value for the gradient. So you've got to follow that instruction. That's a method that they obviously wanted, that is obviously needed there. So last part, describe and explain how the measured value for G would be different if air resistance was not negligible. Well, this is a very hard one. Okay, well, if the value for G was if air resistance was not negligible, that horizontal distance d squared would be less. Okay, so d squared would be less than you normally would have, because the car's being driven horizontally. Yeah. You has anybody else got a blank screen? Can you all see? Right. Yeah. You need to have a look at your settings on Zoom. It might be that you've got the video switched off. Try switching the video on. Okay. So the idea that d squared would be less. So if you drew a graph of h versus d squared, if d squared is less, the gradient would be greater. It would actually be a steeper graph. So if that d squared was less, you'd have a steeper graph. Therefore, G, the measured value for G, would be higher. Okay. It would also not be a straight line graph. If you mentioned one idea that the d squared would be less, or it would take longer to fall, I awarded 1 mark. But this was actually the final answer, and this is actually a really hard question to actually figure out. So I don't blame anybody for losing a mark on that one. Right, now this one is a nice, easy sort of A-level style question. Statements meant by scalar and vector. So a scalar has magnitude, but no direction. And a vector has a magnitude or size and direction. Okay, that's what you needed to actually, that's what you needed to have. That's a very easy 2 marks. I gave that as a bit of a gift for sort of candidates who would be sort of scoring sort of just a pass. So complete figure 1.1 to indicate each of the quantities is a vector or a scalar. Power, well, power is energy over time, both of which are scalars. So that's a scalar. Temperature is also a scalar, it has no direction. But momentum, remember, we know is a vector. Okay. It's basically 2 marks if you got all 3 right, 1 mark if you got 2 right. If you only got 1 right, you didn't get any marks at all. Right, so then we've got an aircraft traveling in wind. Figure 1.2 shows the velocities of the aircraft in still air and for the wind. You're given the velocities, you're given the angles. This is not a scale diagram, but you're asked to calculate. You're asked to first of all draw an arrow on the diagram. It says on the diagram, okay? Not on a separate, not on a sort of a separate bit below the question, to show the resultant velocity of the aircraft. Well, the aircraft is trying to travel that way, but there's also a sort of a northbound component of the wind. So R, that resultant had to be somewhere in between these two angles. So that was what we were looking for. Very few people got that one right. You don't have to draw it precisely because it's only one mark. Oops, sorry, I'll just try and scroll down a bit. There we are. It's only worth one mark. So they're just after the concept, the idea will be somewhere in between this direction and that direction. The next part is to determine the magnitude of the resultant velocity of the aircraft. Now, a lot of you try to use trigonometry here. To be honest with you, what I saw were some good attempts, and where you got it right, and I saw clear working, that was absolutely fine. Doesn't say by drawing a scale diagram, but to be completely honest, I think a scale diagram is a lot easier than trying to calculate it by geometry. So what you do is you draw a scale diagram. So it tells you that the aircraft velocity is horizontal at 95 meters per second. So my scale, I'm going to say that 1 centimeter is going to be 10 meters per second, okay, on my scale diagram. So we're drawing basically our parallelogram, our triangle. So here I've got one scale here. So this is 9.5 centimeters. So start at 0, and I draw it up to 9.5, just there. Oops, it's going that way, not that way. I do apologize. Okay. So that's 95 meters per second. Now, I'm going to draw a faint line just beyond it. You'll see why in a second. Because if I draw a scale diagram, it tells me that the wind velocity is 28 meters per second at 65 degrees to horizontal. So I'm going to draw that wind direction. It's going that way. It shows you in the diagram. It's going that way. So I draw if you draw it to scale, you've got to draw it as accurately as you possibly can. That's 65 degrees to the horizontal. So it's there, 60, whoops, try and draw it as accurate as I possibly can here. There we go. Make a little mark. And that's the wind direction there. So you draw your arrows end to end. Start off with your faint line. Then it's 28 meters per second. So that's 2. So as it's 10 meters per second is 1 centimeter, you're looking for 2.8 centimeters. So you line up your 0 there, and that's 2.8 is about there. So there is your wind's direction, okay, end to end. And the resultant is going from start to finish. There. That's the resultant. Okay. Now you measure the length of the resultant, and when I measured it, I got 100, and the resultant is actually 11 centimeters, which implies a speed of 110 meters per second. Okay. Now, if it was slightly off because it was drawn by a scale diagram, I was fine about it. Some of you tried to use trigonometry, bit of a high risk approach, but it does work. You can calculate the vertical and horizontal components of the wind direction, and then you can add the horizontal component to 95 to get your sort of your one side of your triangle. To get the other side of your triangle, you then square it and you add the square of the vertical component, and you can do it by Pythagoras theorem. To be honest, it's perfectly doable. Most of you have the geometry skills to do it. but I think it's harder. You might as well choose the easy way if the easy way is works and is valid. Okay.
Mr. Gary?
Yes. Yes.
The cosine rule is also okay as well, right?
Yeah, absolutely. If you're using valid geometry, that's absolutely fine. So you're sort of using that sort of a squared plus b squared cosine theta or something like that, isn't it?
Yeah.
Yeah. So that's absolutely fine. That's absolutely fine. It works out just as well. You can do it by any geometric method, but remember what I say about the exams. If you use the correct treatment, you get the marks. It's one of the reasons why showing working is so important, because if you use the correct treatment that I hadn't sort of predicted that people would use, then you might not get you might not get the mark if I can't see where you got your answer from. So it's just very, very important to make sure that you are using showing that working. Okay, everyone, all okay so far? I'm assuming that you are. You're either okay or you're unconscious. Now, where were we? Yeah, so number 6. So this is our last sort of long answer question, I think. You're given a moments question. You know that in the Unit 2 paper, you will always get a moments question. Here we've got the Cantilever Bridge. You'll either get something about balancing levers and seesaws, or you'll get a Cantilever Bridge. That's the most common type of question you'll get. So a uniform plank bridge, it's got a length of 5 meters. Now, if it's uniform, then that way acting. Yes.
How about the mass, the block on the slope question? I've not seen that for a while. I'm like, is it possible that we'll get that?
The friction force on a slope.
Yes.
You might possibly get something like that. Yes, but that's just vectors.
Oh, okay.
That's it. That would be your vector question, wouldn't it?
Yeah.
Okay. So we've got a moments question here. We've got a uniform length. So if it's uniform, that is going to be that weight is going to be acting not 5 meters away. It's going to be acting 2.5 meters away. So again, as I always say, nothing wrong with annotating your diagram. Okay, if it's uniform, center of mass or center of gravity will be in the middle. So that's before we've even read what the question is asking us. It tells you that a man with a weight of 880 newtons stands at a distance x from end A. The ground exerts a vertical force Fa on the plank at one end and Fb on the plank at the other end. As the man moves along the plank is always in equilibrium. Explain why the sum of the forces Fa and Fb is constant no matter where the man stands on the plank. So the idea is that if it's in equilibrium, the upwards force must equal the downwards force. Okay, so the upwards force is, well, the only upwards forces on this diagram are Fa and Fb. So in that case, if Fa and Fb are equal, the downwards force is going to be 800 plus 200. 880, sorry, plus 200, which is constant. Okay, 1 mark if you just said the force, the upwards force equals the downwards force. 2nd mark if you then said that it then sort of if you then qualified it somehow. You could also include the idea the sum, that sigma always means sum, doesn't it? The sum of all forces equals 0. Okay. Some of you started talking about the principle of moments. Yes, it's relevant to the question, but it's not what the question was asking. And a lot of people made mistakes with that. Now, the next one, next part of the question says the man stands at a distance x at 0.5 meters away from A. You have to use the principal moments to calculate the magnitude of FB. So we're trying to find out that force there. So what we have to do, if we want to work out the force there, we have to take the moments about A. So that's the first thing we do. First thing you write. This is something that's often missing when I see answers. We skip the explanation step. We take the moments about A. So we ignore the force from A for now, okay? Because if you think about it, if you take the moments from A, FA times a distance of 0 is just 0, so it just disappears. So we want to work out the idea, want to use the principle of conservation of moments. So we know that the clockwise moments equals the anti-clockwise moments. So trying to turn this clockwise, if we take our pivots here, there's your pivot. So everything trying to turn it clockwise is the weight of the man plus the weight of the plank. So the weight of the man is 800 and x, that distance x is 0.5. So 0.5, there's your distance, multiplied by his weight, which is 880, plus, then you've got the moment created by the weight of the bridge, which is also trying to turn the whole thing clockwise, which is 200 multiplied by 2.5. So that's the clockwise moment. The anti-clockwise moment, well, if you take your pivot about A, the only thing trying to turn this anti-clockwise in the opposite direction to a clock is going to be sort of that force FB, and FB is acting 5 meters away. We don't know what FB is because we're trying to work it out. But the moment from FB is going to be the force FB multiplied by 5. If that's the case, then we're just doing some basic calculations. Well, this part here was 440. This is 500. So it's 440 plus 500. We've got to divide both sides by 5. So we show our rearrangement, we show our calculation, and then you just calculate it, and it comes out to be 188 newtons. Okay. Now it doesn't matter about positives and negatives because we're just looking at magnitudes really. Right. The next thing to think about, and this was not so well answered, so I'm going to spend a bit of time on this, was completing the graph. Now, how do we know that we want something more than just a shape? Well, the big clue is in the number of marks. If it's 3 marks, we're looking for some detail. We're probably looking for some quantitative information. Now, what we have to do is we have to think about, that's the force on FA. Now we know that FB, when the distance is 0.5, so it's about here, we know it's 188. So there's 100, 188 round about there-ish, but that's not terribly helpful to us. We've got to think carefully about how this, about how this will actually sort of pan out. So obviously, when we look at this, when the person is stood at FA, when the person is stood at FA, then obviously they're not going to be exerting any moment if you take FA to be a pivot. So FB will just be the moment created, will just be the force required to balance the moment from the bridge, which, as it's twice the distance away than the center of mass of the bridge, is going to be half the force. So it starts at 200 newtons, half of that is 100 newtons. It then stands to reason when they're at FB, if they stand at FB, then all their weight, then FB is going to be needed to overcome their weight and the force downwards from the bridge, which is going to stay the same. So it's still going to be 100 newtons plus their weight, which is 880. So so but 100 plus 880, which is 980. So 980 is going to be about there. So we're looking for a straight line that's got a positive gradient for 1 mark. And it should be a mirror image, really, of the line being drawn. If you think about it, every time we know that FA plus FB is equal to some constant. So here, if FA is 980, okay, then FB and FB is 200, then we add them together, we end up with 1,180, okay? So if that's the case, that's going to have to be 1,180 minus 980, which would be 100. And here it would be exactly the same, but just opposite. The idea, we start off with 100, we've got a 1,108, sorry, 1,080, I do apologize. So we end up with 1,080 minus 100 is 980, okay? And that's how you work it out. So you know that all the time when you add these two numbers together, for any position of X, it's going to be the two numbers added together from the graph, the readings on the graph are going to be the same. So really it was 1 mark for the gradient, 1 mark for the straight line in sort of, with a positive gradient, 1 mark for showing it sort of crossing the y-axis at about 100, and 1 mark for showing it going to a maximum of somewhere between 950 and 1,000. Anywhere between there was fine. And that's where a lot of marks were lost. It was just thinking through that level of accuracy. And I think it's born out of a misunderstanding as to what was required. If it's 3 marks, you've got to start thinking about some of the numbers involved when you're sketching a graph. The confusion is caused also by the question saying sketch. That means you're not drawing a graph with multiple points. You're just drawing a graph maybe from 2 points. So looking for the graph crossing a couple of key sort of points on the graph paper and being the right shape. And that's where a few marks were lost. Right, we're almost done. We're almost done. So section B is multiple guess, multiple choice. Now, again, I need to go over this one in detail because a lot of people made mistakes here. Remember, the acceleration is the gradient of a velocity time graph. That was discussed last week, I think. Now, if the acceleration is the gradient of a velocity time graph, excuse me, then if we think about it, what we're looking for here is the acceleration is increasing. So as the acceleration is increasing, we're looking for an increasing gradient. Here, the acceleration is decreasing, so we're looking for a decreasing gradient. The acceleration is always positive. You can see this number here, it's always above the axis, so it's always positive. So any sort of suggested graph with a negative gradient is definitely out of the question because you've got a negative gradient there, got a negative gradient there. So they're definitely not right. Then you look at what the gradient's doing. Well, if it's the value of acceleration gives you the gradient, you're expected to get steeper and steeper and steeper and steeper, and then shallower and shallower and shallower. So this one is just getting steeper. So that's not right either. A is correct because at that sort of halfway mark, up until the halfway mark, the gradient was getting greater. And after the halfway mark, it was becoming shallower. So the gradient was decreasing. So A was the answer. Not an easy one to work out, but if you apply your logic, it actually does make sense. Right, this next one was also not terribly well answered. I'm going to go over this in some detail. You've got a ball being released from time 0. After 1 second, it bounces inelastically from a horizontal surface and rebounds, reaching the top of its bounce after 1.5 seconds. So what you need to do is work out the displacement of the ball from its original position after 1.5 seconds. Now remember, if you've got a velocity time graph, displacement is the same as the area under the graph. So the area under the graph is represented by two triangles. We've got this triangle here, and we've got this triangle here. So if we work out the area of these two triangles, well, a triangle is a half base times height. So it's 1 times 10 divided by 2 gives you 5. And here the base is 1.5 divided by multiplied by 5 and then divided by 2 gives you 1.25 meters. Okay. Now the mistake people made was they forgot that it's displacement. Displacement is a vector. Now, if it's a vector, you've got to think about direction. And you've got to think about what's actually happening. If the ball bounces, if I draw the ball bouncing, it starts off at a height h there. It goes down, hits the ground, and bounces back up again. Okay? And it wants to know this vertical displacement there. Okay? So if you think about it, what you're trying to do is you're taking this distance is a distance it's gone down, and in this part of the distance it's gone up. So what we're trying to do is we're recognizing that that is 5 meters and that is 1.25 meters. So you want to know that bit. So it's 5 minus 1.25, which comes out to be 3.75 meters. Okay, because it wants the displacement, not the total distance traveled. So it's the distance from start to finish. Okay, not an easy one. You had to think about that one, and not many people got that one right. Okay, it was a tough one. I did tell you in the description this was a tough paper. Right, the next one, equilibrium and vectors. When we started off with vectors, we learned that if something's in equilibrium, if everything's balanced, then it forms, then if you put the force vectors end to end, then they should form a complete triangle. So we've got to think about direction of forces. The direction of force on P. So we've got the weight of the cable car, okay, trying to act downwards. The tension of the cable is trying to pull it that way. This cable is trying to pull that way, okay. So if we're thinking about it like that, what we've got is we have to put our arrows end to end. So P is acting downwards, okay. The weight is W is acting downwards. If we think about it, we've also we could add that on. If we've got this cable here is acting down and to the left. So you have to put your force arrows end to end. And this cable here, T1, is acting up and to the right. To prove that something's in equilibrium, when you put your vectors end to end in a scale diagram, they should form a closed shape, okay, no gaps. So once we've done that, you can then start to compare, once you've sketched, you can then start to compare with your actual answer here. So T1's acting upwards, so T2, I do apologize, yeah, T1, that's right. Okay, T1's acting upwards. Well, we've got to think about whether or not we've done this correctly. So let's have a quick look. The T2's acting that way. Well, they've kind of drawn it as a bit of a mirror image. They've kind of put them on the other side. So first thing we can do is look for any examples where the arrows aren't placed end to end. So T2, T1, well, that's not placed end to end, so that's not right. If we look at this one, they are placed end to end, so that's a possibility. In this one, are they placed end to end? Yes. Are these placed end to end? Let's have a look. Then down, up, right, down, yeah. This one, down, up. That's not end to end. That's not right. In this case, down, not end to end, not right. So the answer is B. Okay. So what we then do is that tells us, gives the answer straight away. The only difference between that diagram and my diagram was, instead of putting T2 on that side, what they did was they've had the weight and they had T1 acting on this side. So you're completing a parallelogram basically. But either way, you've got a complete parallelogram there. Okay. Now, last one, you've got, this was to do with the multiples. A couple of you showed a little bit of misunderstanding with what some of the prefixes mean. Okay, just a reminder, I always think of it as tera, giga, mega, kilo, and then you've got milli, micro, nano, and pico. And remember that we start off at 10 to the power 12 and go down in threes. Okay, and then you're just using your mnemonic to remember the order. 10 girls made kind men microwave nice pizzas, something like that. Okay, so if that's the case, we're looking at pico, which is here, and we're looking at giga, which is here. So giga is times 10 to the power 9. 10 to the power 12 is tera, as in a terawatt, or as opposed to a gigawatt. And pico is times 10 to the minus 12. So the only one that's actually correct there is C. All okay with that? Okay, so what we're going to do next is basically we've got about 15 minutes left. If you need that. Does anybody have any questions? No? Right, well, I'm going to give you some final advice for the exam, okay? My final words about the exam paper, about the final exam. The questions will probably appear quite familiar to you because you've done so many practice questions that if you've done all 8 practices, you'll probably recognise the odd question anyway. But hopefully they'll be different to the ones that I gave you, but they'll be very, very similar. First step. Step 1. You've got plenty of time. You've got an hour and a half. Start by having a read through the whole paper. The reason why you read the whole paper first is you'll be able to spot straight away questions that you know will be easy. So you know that so you'll get that confidence that you'll be able to do some of the paper. Okay, so if maybe the first couple of questions you're struggling with, if you haven't read the whole paper, it can undermine your confidence a little bit and make you start to give up, which we shouldn't. You read the whole paper, you know the questions coming up that you can do. do the easy questions first. Okay, skip the hard ones and just do the easy ones, the ones you know you can answer straight away. Okay, do the ones you're best at first. So for some people, actually, I know when I was doing A-level physics, the questions I found easiest were usually ones involving graphs. So I did my graph questions first. So do the easy questions first. The other reason to be doing that is because you've read the whole paper, the part of your brain that you're not aware of, called the subconscious, starts to process some of the harder questions. It starts to actually process it without you knowing about it. So if you read the whole paper, then do the easy questions first, your subconscious gets to work on the harder questions and the questions that might require some figuring out. So when you come to do the harder questions, then you're more likely to have a better idea as to how to tackle them. Step 3. Check your calculations. Okay, do your calculations twice. You've seen when I've done walkthroughs that it's very, very easy to just miscalculate something. So just double check it. Make sure that when you calculate something, you've put it correctly into your calculator. Your calculator is like anything else with the keyboard. We're prone to making typographical errors. So make sure you've checked your calculations. I saw a couple of cases when I was marking this last paper where people lost marks because they did the correct technique, but just didn't do the calculation correctly. And it was literally that I could see the button that they'd accidentally pressed on their calculator. It's a dreadful shame. It's a silly thing to lose a mark over. Number 4, show you're working. Show some working. 2 reasons. First of all, some questions require it. You don't get full marks unless you do show you're working. The other reason is that if you make a mistake, then if I can see what you did and see you along the right lines, you should be able to get some credit for that. So showing you're working. So I have to say, with the practices I've seen you do, it's not been bad. It's not been bad at all. So so you have been pretty good with showing you're working. Remember, if you get a question which says show, you should annotate that working as well. Make it as clear as possible as to exactly what you did. Okay. Okay. Next thing, the last thing is use all the time available to you. You know that for the first, I think the first half an hour and the last half an hour, I think it is, I can't remember what Mrs. Randon said now, but for the first half an hour, the last half an hour, you can't get up and go to the toilet, you can't leave the exam room early. So use all the time, okay? If you've checked your work, check your work again. It's so easy to make a little mistake. Pay attention to things like marks. How many marks are for a question? Have you said enough or done enough to earn those marks? If it's a 3-mark graph question, you know you've got to put some values on. If it's an explanation, if it says explain and it's worth 2 marks, you know you've got to go into a little bit of detail. But if it's explain or state and it's only worth 1 mark, you know a simple statement will do. Okay. The other thing while you're doing the exam is think about your command or action words. Like state, which means just state something simply. There's not usually much no calculations you have to do. Describe, which means describe what something is, okay, or what will happen, which is different to explain, which is to say why it happens. So that's the difference between describe and explain. Discuss or evaluate means to actually, which means to actually look at something and draw a particular conclusion about it. So, for example, you have to discuss whether or not something is is an equilibrium. It's very similar to suggest. Suggest, remember, means to say whether or not to sort of give an answer and explain why. Okay, so those are your key action words. Make sure you're following the action words, and be very careful to make sure you are reading that question carefully and make sure you understand what the question's really asking you to do. Okay. Number 7, last one, lucky 7. And this is where historically, not just you as a group, not you as an individual, but this is where pupils, where students fall down the most. I always say attempt all questions, even if you don't have a clue, come up with something relevant to it, because there are 2 reasons. First of all, if you don't attempt a question, if you leave it blank, you're guaranteed not to get the mark for your answer. If you attempt the question and you make a mess of it, you still get no marks. So you've lost nothing by attempting the question. And I don't deduct marks for incorrect answers. So you lose nothing by attempting the question. If you attempt the question, you start writing something relevant, what you write then might be enough to get you a mark. Say for example, if it's a 3-mark question, you might get 1 out of the 3 marks. Well, okay, I want to aim for more than 1 out of 3, but in the event where you're likely to get 0 if you don't write anything, 1 out of 3 is 1 more than 0. The other reason to attempt all questions, particularly even if you're not sure what to do, is as you start to attempt it, you start thinking a little bit more about it. And as you start thinking a bit more about it, sometimes the answer, the answer or how to arrive at the answer can come to you. So it's important to attempt all questions. I find nothing more disappointing than seeing blanks in answer spaces. Okay. The last addendum is really to those of you who are taking exams remotely, which according to my records is just 2 of you. If you're a day student or you're a boarder and you're in Market Harborough, then you should be going to the King's Hall next week for your exams. If you're not a day student and you are not in the country, then obviously you've applied to take your exams remotely, for which you should have received a declaration form to sign. When you are if you are attempting remotely, please save it as a PDF file. You must save it as a PDF, not as a series of pictures. The reason being is that there are a lot of papers to process. If you save it as a series of pictures, when it comes out of the printer, it comes out in a funny order, and it makes it very, very difficult to actually mark, which means you're less likely to get full marks. So you save it as a PDF. If you have to save it as pictures, please put your name on each page. The reason being is, again, not with practice 8 so much, but with practice 7, a lot of the pages came out of the printer in a funny order, and it was just impossible. And there were certain questions where I couldn't tell who had actually answered it, so I had to kind of guess. So your grade for practice 7, unless you sent it as a PDF, I'm afraid had to end up being estimated based on what I could definitely see. Excuse me. Okay, so that's the only last bits of advice. Anybody got any last questions? You've got a couple of more minutes. Anybody?
Gary?
Yeah.
Do you have any apps that you know that we can use to scan out work as a PDF file?
Yeah. Well, I mean, Owen, you're going to be in the exam room, aren't you?
Yeah, I would, but I'm just asking because I never knew how to do it for.
You don't have to worry about that. You'll have a paper. Those of you who are working remotely, who are going to be doing your exam remotely, if you look in the instructions I gave you along with the declaration, you'll see that I've suggested a PDF scanner app. Basically, if you go on the App Store or Google Play, if you Google PDF scanner, you can usually find different scanning software that will save your file as a PDF, and it just helps to keep the pages in the right order, and means that you're more likely to get the right mark for your work. Okay. Any other questions? Nout? Okay, well, I'll say this to you. Best of luck for next week, although luck doesn't enter into it. If you've done, I've seen lots of practice being done. If this is your practice work and that's the standard you're going to work at, most of you are going to eat this exam up. You're going to be absolutely fine. But if you have not done enough revision or you've not been trying the papers, then you might have a few difficulties. It's all down to how much work you've done. Look through your revision, your student guide. Look through the checklist at the beginning of the student guide to see exactly how much, exactly what you need to make sure you know about. Go through some of the walkthroughs. If you go back over Show My Homework at the previous tasks where I have done a walkthrough lesson, I've recorded most of them. You can watch them and you can just make sure that you understand how to answer the questions, and you'll be fine. You'll be absolutely fine. So best of luck for next week. Don't forget periods 1 and 2 are cancelled for lesson wise. Period 3 onwards, don't forget that you are in, you should be in your lesson. You should be in your lesson if you're not in an exam. You can't be just sort of wandering around. It's not productive. When you're in the lesson though, you will be expected to do some revision for your up and coming exams. So for example, if say on Wednesday's lesson, you've got me period 3 and 4, you're expected to be in the classroom period 3 and 4 in my classroom. However, you should be doing just your own revision. But as you've got a physics exam the next day, you might want to use some of that time in the classroom to ask me questions. Okay, have a good weekend and best of luck with your exams next week. Take care, everyone.